Hello geometry students, it's Mrs. Davitt here. Today we're going to dive into choosing a tool. So we're going to be looking at a variety of problems and trying to decide which of our existing triangle tools is best fit for the situation. So let's start by taking a look at the different types of tools we have. Now, we have looked at a bunch of tools that apply to right triangles as well as some that apply to any triangles regardless of whether they have a right angle or not. So I want you to pause this slide and brainstorm on your own which tools have we learned so far that deal with right triangles and which apply to any type of triangle regardless of whether it has a right angle. So take a minute, pause, and brainstorm yourself, please. And we're back. So hopefully you have a list similar to mine. We started out in right triangle world where we learned things like Pythagorean theorem. Now, Pythagorean theorem lets us talk specifically about right triangles, and it lets us discuss relating the three side lengths. So if we know any two sides of a right triangle, we can use Pythagorean theorem to find the third side. Right triangle trig is a little bit different. Now, we sometimes call this SOHCAHTOA, and this allows us to relate any two sides of the triangle to one angle. So if we know the angle and one of the sides, we can find a second side. Inverse trig is very similar in that it also relates two sides and one angle, but usually here we'd be solving for an angle. So you'll see things like sine inverse, cosine inverse, and tangent inverse. These relationships let us undo the traditional sine, cosine, or tangent functions to find an angle. Most recently, we learned about special right triangles. Special right triangles occur with certain specific angle relationships, either 30, 60, 90 degree angles or 45, 45, 90 degree angles. And as we saw with these triangles, their side lengths always occur in a certain special proportion to each other based on the angle measurements. You may have also noticed a bunch of triangles that we refer to as Pythagorean triples. These are right triangles that occur in nice whole number side relationships like 3, 4, 5, 5, 12, 13, or other groups of triples, but they would always occur either as those numbers or proportional triangles, meaning some scale factor version of those triangles. You may have noticed those in some of the examples that you've done. If you've gotten nice whole number sides for all three sides when using Pythagorean theorem, you were discovering a Pythagorean triple. So you may notice that on our any triangle side, we only have two tools. That means there are only two things we need to consider if we're trying to solve a triangle that is not a right triangle. The first is law of sines, and that can be used to find sides or angles. And the second is law of cosines. Now, to take a look and figure out when we might use one of these tools versus the other, it's helpful to look at the formulas. Now, this is the general formula for law of sines, and as you can see, it shows three separate ratios here. But typically, we're only working with any two of these ratios. So sine of A over side A and sine of angle B over side B would be one version of this relationship. Law of sines is helpful when we're relating two sides and the angles opposite those sides. You can see that in the formula because angle A should be opening up to side A, meaning side A is opposite angle A. And angle B should be opening up to side B in the triangle, meaning that side B is opposite angle B. So if you are looking at a non-right triangle and you have two sides and two angles that you're trying to relate and they're positioned opposite each other, and one of those four pieces, either side or angle, is missing, then you want to use law of sines. So think about that. You're trying to relate two angles and the sides opposite, and you're missing either a side or an angle in one of those two proportions. That's when we use law of sines. So when do we use law of cosines? Well, again, the formula is helpful in cluing us in here. Again, we're working with any triangle, so it does not have to have a right angle, but you can see in the formula that we have three sides, A, B, and C, and one angle, angle C. So what's important here is, first of all, we are relating 3 sides and 1 angle instead of 2 angles and 2 sides like in law of sines. And this angle occurs opposite this side. Okay, so if you're putting some side length here, you better be putting the angle that opens up to that side over here in the formula. So that's helpful because sometimes we might use an alternate form of this formula where we kind of rearrange the letters, and maybe this is a squared, but then this should be angle A. And then anywhere you see A, you would just sub in C, the other side. So it's really important that we're positioning our terms properly when using law of cosines. Now, in law of cosines, you could be solving for side C, and that's actually probably the easiest of all the formulas here for our non-right triangles, because then everything here would be known to us and just be written in, and you would just be having C squared equal to that quantity. But you could also be solving for angle C, in which case you would know C, A, B, and the A and B here, but you'd have to undo a whole lot of stuff to solve for angle C. So hopefully that gives you a little background on when we use which tools, especially our newer tools for non-right triangles. So let's dive into a few examples. Take a minute to read our first example here. This is one of our book problems, and see if you can label the sides in the diagram that's given to us in order to set ourselves up for our next triangle problem. So in this problem, we are looking for the distance across the lake, which I've labeled x. We know angle C, 53 degrees, angle B, 79 degrees, and the length of segment AB, which is 684 feet. So what I've done is I've set up the diagram and then set up a larger scale version of the diagram that we can use down here. So let's take a look at what we have. We have an angle, C, and the side opposite that angle, and we have another angle, B, and the side opposite that angle is the one we want to know. This is a non-right triangle, so the only two tools I can consider are law of sines or law of cosines. And looking at the pairing here, angle, side opposite, I'm thinking of using, you guessed it, law of sines. So let's get started. So I'm using this version of the formula simply because we know that in our triangle, these angles and sides are labeled B and C. So let's plug in the values that we know. We know angle B is 79 degrees, and side B is what we don't know. We know angle C is 53 degrees, and we know side C, which is segment AB, which is 684 feet. Now, when we're solving law of sines, we're going to cross multiply. So that means we're going to do x times the sine of 53, and that should be equal to 684 times the sine of 79. From here, to solve for x, we need to undo this sine of 53. So we're going to divide both sides by the sine of 53. On this side, it simply reduces. It makes like a 1 pair. And on this side, we actually have our answer in exact form. But to go ahead and solve it, we'll just type that into the calculator. So we're going to plug all of that in, 684 times sine of 79, all of that divided by the sine of 53, and see what we get. So when I type that into my calculator, and again, a quick reminder, making sure that I am in degree mode, I got 840.73 feet, and that's an approximate answer, so I should modify my equal sign to be a little squiggly equal sign to show that I rounded. Now I can do a quick visual check here to make sure this makes sense. Think about our diagram. This angle over here, 53 degrees, opens to this side length that we knew, 684 feet. This angle 79 should open to a larger side length, so that checks out with our answer. We got 840.73 feet, and that is larger than the 684 that we knew. Awesome. On to the next example. So take a moment to read this example It's the same lake, but some different scenarios here, and see if you can label up the diagram and decide which tool you're going to use. So the information we're presented with here is a little bit different, but in this case we are given the distance between A and D, which is that 800 feet. We're given the distance between C and D, which is that 694 feet, and then we're also given the angle D, which is the 68 degrees. So looking at this, they still want us to be checking the distance between A and C, right here where we would be building our bridge. So in my bigger diagram, I've labeled that X. That's my unknown. Now, taking a look at this triangle, we should notice that in this scenario, we again have a non-right triangle, but we're relating three sides, one of which we don't know, and an angle. And the good news here is the angle that we're relating is opposite the side we want to know. So this looks like a perfect candidate for law of cosines. So here I've written our general formula for law of cosines, law of cosines, c squared equals a squared plus b squared minus 2ab cosine c. And then I've rewritten it to fit our triangle just so we're not confused. So in this case, we're trying to find side D. So we're going to use d squared to represent that part of the formula. And then we know sides A and C, and we know angle D. So let's go ahead and plug in our values and see where we're at. So D, the side length, is the value that we don't know. So I'm just going to put in my X. You could also leave it as D squared. We know side length A, it's opposite angle A, so that's the 694. We know C, it's 800. And then here, minus 2A, so that's our 694 again. C, that's our 800. And angle D, we also know, cosine of 68. Now this formula looks really complex, but the good news here is we know all of these values. So we can actually type all of those into the calculator and get x squared right away. When I do that, I get 705,672.838671. And then to solve for x, or for d, we're just going to square root both sides. And when we do that, we get approximately 840.04 feet. Now, we're asked in this problem to see if it verifies our answer from the last problem. So if we look back at our last problem, we got 840.73 feet. So this is not so far off from our answer here. We can probably chalk up the difference just to human error in measuring these sides. So hopefully these two examples helped show the differences between when we use law of sines and law of cosines, and helped you think a little bit more about when we use any of our triangle tools. Thanks for joining me.